Thanks to the organizers for inviting me. I'm a postdoc with Peter L. here Latham in Gatsby, and last year I got to be a spectator at this meeting, so it's nice to be able to talk and contribute in a small way this year. And the work I'm going to present is some really simple stuff, so I thought it would be a lot more fun and engaging if I just wrote it out for you rather than flashing equations. So please feel free to ask questions as we go, and I'll do my best to answer them. Now, Idan yesterday, he was talking about the cortex and trying to explain this jungle. And we are also dealing with the jungle, with our own jungle. Our jungle is a little bit smaller, and this jungle is the olfactory bulb. So all of this work was kind of motivated in trying to explain anatomy and to some extent the dynamics of this system, but it's quite general. So I'm going to present it in a general setting, but all the motivation is essentially geared at trying to understand a neural system. Now this morning I checked that all of these markers are working, so and I was sitting at the back there yesterday, so I'll try to write very big so everyone can see. The outline of my talk is going to be covering 5 simple points. So the first one is the problem that we're going to try to address, and that's going to be doing maximum a posteriori inference in a really simple linear model, basically as simple as you can get. And because we're interested in how neurons do this, we're going to try to solve this problem using gradient descent, because that's, neurons can do that for the simplest models that we're going to talk about. So I'll show you kind of a simple, I'll just basically take the gradient, and we'll look at that. And this will imply a circuit that I call the sparse coding circuit, just because that's basically Olshausen and Field's implementation in their paper. And then this will bring us to the problem that we're trying to address. And that problem is that when we look at what this circuit implies in terms of connectivity, we'll see that certain units are going to have to be connected essentially in an all-to-all manner to certain other units. And because in the olfactory context there are so many of these other units, it's going to imply one cell connecting to, let's say, 1 million others. Or if the connectivity isn't quite so dense, maybe 100,000 others. And that seems like a problem that we should try to fix. So the problem is going to be, I'm just going to call it all-to-all connectivity, but it doesn't necessarily have to be so bad. Okay, and now the solution. So these days, whenever you have a problem,
I'm sorry, I still don't understand why I have a problem.
You will understand.
Okay.
Okay, but the problem is going to be that when we write out, this circuit diagram for what to do gradient descent, you'll have cells that are connected, individual cells connected to millions of other cells.
So gradient descent for what?
Gradient descent on an objective, that's going to solve the map. So it's the map objective. Yeah, so you'll see. Right, so we have this all-to-all connectivity problem, and just like we do on the internet these days, we're going to solve it with one weird trick. And that one weird trick is going to be turning an unconstrained optimization problem and solving it as a constrained optimization problem in a higher dimensional space. So we're going to do this, and I'm going to apply this to the original map problem. So map as constrained optimization. And this will give us a circuit that basically looks like a predictive coding solution, where essentially what's driving the output neurons is some error residual. But this will still have this problem that I will talk about. So then I will take inspiration from this property in the olfactory bulb of the sister mitral cells, cells that share their inputs but have different basal connectivity to the granule cells. So I'll introduce the sister mitral cells, and I'll use them to solve map as constrained optimization itself as another constrained optimization. And then I'll show you the circuit for how that works. And we'll see that it looks like the actual thing to a large extent. Then if we have some time, I'll show you one final addition to this model. And if we still have time, I will then draw you some performance plots. So that's what we're going to do today. Okay. And if you actually want to see the real performance plots, I can show them to you on my computer after. All right. So part one. So map in a linear model. Okay. So suppose you have some unobserved variable x, and this is, for us, is going to be some odor vector, so a high-dimensional vector of positive values, for example, and it's drawn from some distribution p of x, and this could be a sparsity promoting distribution. For most of the talk, it won't really matter. But you don't observe x. The animal is not going to observe the actual odor itself. It's going to observe. We're going to assume a linear projection of the odor, a lower dimensional linear projection. So maybe if x is n-dimensional, and this is I don't know, let's say 1,000,000 dimensions, y is going to be much smaller dimensions. So maybe it's going to be m-dimensional, and it's going to be 10 to the 3, let's say. And we don't observe just this linear projection. We'll also add some noise, some just Gaussian isotropic noise with variance sigma squared.
In the context of a function, what would be this number?
Sure. Okay, so in the context of a fraction, x is going to be a vector of molecules. So the x-axis is a vector of molecules, and x is going to be the relative concentrations of these molecules in an odor. And so that's kind of what inspired this work. So if you actually go and so on the y-axis here, we have the molecular concentration. So x is this vector of values. So if you actually go out and look at for real odors, what this looks like, you'll see that this is actually a very sparse vector. So there are a few molecules that are at high concentrations, the rest are essentially absent.
And why?
Y is going to be the glomerular activations. So and this is, in the vertebrate we have about 1,000 of those glomeruli. So again, that's the olfactory case. And that's why I put on these these numbers.
So how realistic is linear?
Not realistic at all. But
there's an intermediate regime where it works okay.
Right. Yeah.
It's very low and very high.
Yeah, because so it will work in the intermediate regime, but the olfaction also has these competition, saturation. So this is all it's kind of the first order model. Okay, and we're just going to say that the way we're going to estimate x from y is we're going to do map inference. So that's going to be at the output of this system, let's say in the granule cells or in the piriform cortex, we're going to say x is going to be the arg max over all possible odors of log of px given y. Okay, and if we actually do this, it's going to be we're going to be minimizing some function, so it's going to be arg min of some phi of x, and this will be the negative log probability of this, which for now is just not going to matter, and some contribution from your observation model. Okay, so very simple. Okay.
And you optimize over x? No,
over x. A is fixed. Oh, and A is good. Let's just talk about A is. So A is a short fat matrix, and it has let's say in our case m by n dimensions, and Aij is going to be the response of a particular glomerulus, the ith glomerulus, to the jth molecule. So we're just going to assume this is just fixed.
Random?
In my simulations, yes. In real life, it's just what the receptors do.
So I don't understand what is x. I mean, so you choose this is the texture problem.
It's exactly what the sparse coding problem. This is exactly sparse coding. So Aij is going to be some value that I'm just going to pick.
I have a question.
Yeah.
What the brain has to do, the brain doesn't care about it, right? It cares about the identity of an order.
Everyone always asks this. So,
why? Okay.
so that's why I didn't want to bring in the olfactory context too much. But So my solution, people ask me this, is I think what actually happens is you get this dense vector, the system first splits it into its components, and then the downstream area will then learn the objects from that. But you could also think about it differently. You could say, well, this vector of molecular concentrations is actually, they're not molecules on the x-axis, they're objects. And objects are presumably also sparse in olfactory space. But so in that case, then you would have to learn A. You wouldn't just know.
5x is the probability distribution of the x's?
Yeah, it's prior to the log.
Could you tell us what it is? I mean, what's your sum of that?
I will, yeah. But so for right now, it's not going to matter. Later, I'll tell you what it is. And the reason why it's not going to matter right now is because essentially, okay. So what we're going to do is we're now going to do gradient descent on this. So I'll just go back on this side, erase all this. And okay, so let's assume that 5x, like in the sparse coding setting, 5x was differentiable. So we're gonna say, look, we're going to assume that there are some neurons in our system that are trying to compute this, and we're going to map the elements of x to the activity of the neurons. And we're going to say, okay, they're going to have some time constant, and these are all vectors, and their activation response to an odor is going to be proportional to, I'm going to call this whole thing 5x, the negative gradient on that of x. And when we actually write this out, there's going to be a what's that?
So there's a neuron charge of each chemical?
Exactly. There's one neuron corresponding to each chemical.
It's not the same X, it's like the estimated optimized.
So when this thing converges, that will be the optimal x. So this is, so it's kind of a little, these are neurons, but they will correspond to molecules, and when the thing stops, you're going to have the vector load. And so you're going to get some term that's going to be, the d phi dx, and this thing is going to be, will often be like a leak term, and its form will vary based on phi, so that's why right now it doesn't matter. Plus A transpose y minus 1 over sigma squared, and the sigma squareds don't really matter, but I'm just going to keep them around.
So you assume phi is smooth?
In this case I do, but for my later work I don't. It'll have the yellow one on there.
So phi is just log of p.
Exactly, negative log of p. Yeah.
And so otherwise you don't assume anything about it.
In this case, no.
If it's a Gaussian, of course, it's simple.
Exactly. In the Gaussian, you just follow feet forward, actually, so you don't have to do anything. Yeah. So, and when phi becomes non-differentiable, then you'll have thresholding effects happen, and you'll see that. But for what I want to, I'm putting this out because I want to highlight the problem that will come up. If you just even don't worry about this aspect, just worry about this. So if we actually draw this as a circuit, so let's draw this as a circuit, which is essentially the game we want to do. We want to go from this and make predictions about what the circuit should look like. Okay, so we see that there is what looks like a feed-forward excitation component coming from the Y's, and there's recurrent inhibition. Okay, so what this looks like as a circuit is you've got your glomeruli, let's say, and so this vector of activity is y. So there's some true x out here. It's giving you a vector of activity y, and you're trying to infer it. So you are mapping out to many cells, and this is going to be x. So this whole thing is x. And dynamics are driven by this. And so what does this imply about connectivity? It implies that the feed-forward connectivity to the x's from the y's is A transpose. So that means that each one of these y's, so let's call this yi, has to connect to every single one of these x's according to A1j. So that's basically going to be one row. So this was the A matrix before. So if we take the first row of this matrix, that is the connectivity from this first glomerulus to all of these cells. And in the olfactory setting where this could run in, the size of x could run into the millions, we assume, this means that one glomerulus, or one cell later on, will have to connect to, let's say, a million of these outputs.
Unless H bar.
As A spark. So in real life, I just looked up this morning, for example, how dense is this? they say the recent studies in the rat, for example, say this is about 10 to 30% dense. So now you're not talking connected to a million cells, you're connecting to 100,000. So that still would say, especially for this system, that is a lot, and it's unrealistic. So what we wanted to do was to come up with a way of fixing this problem. Okay, so and in a principled way, so coming up with a system that solves this equation, so the map inference problem, but does it with a sparser connectivity. So that's the optimal connectivity Murav. This problem.
Do you care also about the recurrent connectivity? Which is
Oh yeah, so the recurrent connectivity, that's even worse, but the next circuit I'm going to derive will just be the predictive coding where that essentially goes away. But yes.
But the phi to the x also implies within it some complicated recurrent structure.
So typically these priors they factorize, so this derivative will only involve the x's. Yeah, exactly. Yeah, exactly. So if you have a complicated structure, then, but this again is the simplest small linear, so we won't run into that.
So if you assume factorization of T,
Yeah.
it's kind of one-dimensional model, and you essentially assuming that the chemicals are independent.
Yeah, exactly.
But in reality, I guess there are combinations of them, which really makes it difficult.
You are picking out all the limitations of this model, yes. Yeah. So in real life, they definitely don't factorize, but right. Okay, so now I'm going to so how are we going to solve this problem? So the way we're going to solve this problem is to apply our trick to the map inference problem and come up with a new circuit. So what I'm going to do is I'm going to so I'll just fix everything. And I think I'm still okay for time. Okay. All right. So what we want to do now is we're again going to solve this. So remember that our problem, which I just erased, was to we wanted to minimize f of x. So we wanted to find x dot is equal to argmin over x, which was equal to phi of x plus 1 over 2 sigma squared y minus ax. Okay, so what we're going to do is I'm going to say, look, minimizing this is actually, I'm going to introduce a new variable that's going to capture this residual. I'm going to say minimizing this is the same as minimizing, so it's going to be, and maybe we don't actually need this anymore, f of xr now, which is going to be defined as phi of x plus r squared. Now obviously if I just left this alone as it was, you could just minimize both of these functions to 0. So obviously we need a constraint such that r equals y minus ax. So do you agree that this equals that, right? We just plug in y minus ax into r and you just get these two equations. Okay?
The second line, you say you only minimize over x, but you minimize over both.
Yeah, you minimize over both and you kind of read out r. But r is kind of has some constraints on it. But yeah, so maybe I should have that. But this is the thing we care about. Okay? But the cool thing here is now you've actually separated these two parts of the problem. So we're going to now deal with this constrained optimization. We've gone from unconstrained to a constrained optimization problem. So now we have this kind of such that constraint. And now this is going to give us a Lagrangian. So we have a Lagrangian now over these two variables and a vector of Lagrange multipliers. Okay, so we've got the plus lambda transpose. Okay, and now the method we're going to apply to solving this is called dual ascent in the optimization literature, and it's very simple. So it's based on maximizing a particular function, what's called a dual Lagrangian, which is defined as the infim over x and r. So you plug in your lambda, so your lambda is fixed, and you just minimize this Lagrangian over the others. And why is this important? Why is it an interesting function? Well, the first thing we see is that it will be a lower bound of our optimum value. So this, because we're minimizing over x and r, will be less than the value at the optimum for that value of lambda. And at the optimum, so let's just kind of write this out, what would that look like? So we have our optimum value of x plus 1 over 2 sigma squared, our optimum value of r. And we're, at the optimum, this is going to be 0 because this constraint has to be met. So this last term is going to be y transpose of, and this is just going to go to 0 because this constraint is met. And this term here becomes y minus ax. Okay, so this thing is just f of x. So g of lambda is a lower bound, is always less than or equal to f of x star, and it's another nice property of it is that it's concave. So it looks like this. So here is g of y, g of lambda. And for our kinds of problems, it turns out that, and this will be the optimal value of lambda. So when you maximize this thing, the value that you achieve will be this value. So this inequality becomes an inequality. This inequality becomes an equality. So g of lambda star is equal to f of x. And at that value, you can just read out this value of x that you get in the situation will be the optimal value. Okay, so then that's going to motivate a very simple algorithm. So let me move this over. Okay, so what's that algorithm going to be? So that algorithm, in the discrete setting, the idea is going to be to, let's say you start with some value of x and r that you're going to assume we're. So our job is going to be to, here's the algorithm that people use, and this is the dual ascent algorithm. So given some xt and rt, you're going to say change yt plus 1 is going to equal to y of t plus, some delta t times g of y for those values of, So you update your value of, you're given, you plug in x and t and rt to get g of lambda, and you just update lambda, and then you compute is going to equal to, the argmins over x and r of lambda, x, r, lambda t plus 1. So the idea is you start with some value of, x and t are given, so given, x, t, y, t. You update lambda, then you update x and r, you update lambda, you update x and r, and eventually, you can do the convergence, you'll get to the top. So we're just going to do the continuous, yes?
So G is proportional to 0.
What's that? Oh, sorry, yeah, so it's going to be the gradient. Yeah, sorry.
Free energy.
Yeah, that's right, and that should be, that's right. Sorry, yeah, perfect. Okay, so now we're just going to do this in, the continuous setting. So we're just going to say, look, in the continuous setting, we're just going to have some lambda parameter, whatever it is, and the tau is really different, it doesn't matter, is equal to, it's going to be proportional to, and this g is going to need, g of lambda, but this g is going to need the optimal values of x, and you're just going to, x and r, you're just going to compute those on the fly. So the values of x that you'll plug in will be x of lambda. It's going to be, just be the argmin that you'll compute as you're going. So as you just do this in the continuous setting. So if we actually write this out for our problem, we can see this. So let's go back to our Lagrangian right here. Okay, so the first thing we're going to do is we're going to find what the minimums are for x and r. So we can just get rid of r right away. Okay, so here's our so we want to know, given some lambda, what is our minimum value for x and r. So the first thing we're going to do is we're just going to say, well, if I knew what lambda was, what was the minimum for r? So we say this is going to equal to r over sigma squared minus minus lambda. So this is just, we just set this to 0. Okay. And so now we can just get rid of r from this whole procedure and have it be just in terms of lambda and x. Okay, so we've eliminated one of the variables already. And it turns out that this is going to be equal to, it's going to be, I'm just going to write it squared plus lambda transpose y minus ax. Okay, so the lambda dynamics are just going to be, get whatever the optimal value of x is, and they're just going to be the gradient of this equation. So if we assume that we have the minimum value of x and we plug it in wherever lambda is involved, we get the lambda dot is proportional to the gradient with respect to lambda of, we'll just call it x of lambda. So we're just going to assume this is just some fixed, just a fixed value we're given. And this is going to be equal to minus sigma squared lambda plus, I'm missing a term here. Minus plus y minus ax. Very good. Okay, so that's it. So there's a leak term, there's an excitation term, and there is a feedback term.
So you don't take the gradient with respect to x of lambda?
No, yeah, exactly. So here you're just going to assume that it's fixed. Yeah. Okay. And now for the x. So the x is now we actually have to plug in what phi is, and the phi that we're going to use is going to be a sparsity-inducing phi. So I'm just going to get rid of all of this stuff. Okay, I think we'll be able to, we should be able to get to the second part of it. Okay, so now we need to minimize this thing. So if you're given lambda, minimize L of x lambda with respect to x. So we need to know what phi of x is. The phi of x that we use is going to have an L1 contribution. So it's an elastic net if and there's going to be some barrier function. And this barrier function is just going to impose that x always is non-negative because these are concentrations. So it'll be infinity if x is negative, otherwise it'll be 0. And when we plug that into here, because this is non-differentiable, then you have to deal with subgradients. So I'll just kind of give you what the answer is. So it's not quite as simple as just setting the gradient to 0. But the answer just ends up being a rectified nonlinearity. Okay, so the rectification comes from, just the fact that there is a rectifying process going on comes from this. The fact that it's a positive nonlinearity comes from this. And, the parameters of the sparseness are coming in there and the noise. And then you have a scaling term that's due to two term. Okay? So,
I'm sorry, x is the vector. What is I of x greater than?
so this is just going to be applied. So this is, so exactly. Well, I'm going to say sigma I of xi.
Okay.
And it's just okay, cool. And so this kind of looks like the firing rate of a neuron. So in case we want to make things a little more neurally palatable, what we can just do is introduce a voltage variable, and I'm just going to say tau v is equal to minus v plus a transpose lambda, and then the firing rate of some neuron is going to be a scaled version that's just determined by this voltage, but everything else Okay, so we've got lambda dynamics down here, we've got, our x dynamics up here, and now we can look at, again, as before, what circuit does this imply? And does it solve our problem? Okay, so I'm just going to keep the dynamics equations up, but get rid of everything else. Cool. Okay. So what does this imply? So here again we have, as before, we have our y. So our odor has caused some excitation here. Now we have one-to-one excitation. And these are going to be our lambda variables. So you see, each lambda just interacts with one. Okay, so there's one-to-one excitation, no interaction. What else do these guys get? So the excitations going in, they're going to get inhibition from all of these guys. The feedback inhibition, and similarly for the other, that just I won't pull it in. So that's that's okay. So again, you're getting inhibition from lots of neurons, so that's okay. That's going to be problematic. And what are the V and X dynamics here? So if you just look at this, each one of these terms has a leak and a feed-forward excitation. And then some, there's rectifying nonlinearity on top of it, but that's not going to be important for us because already we've run into the same problem as before. Okay, so we've got A transpose going in this direction, you got A coming back, and you're going to end up having one of these guys talking in the exact same way as before to a million cells. Okay, so we still have the same problem. This kind of looks like a predictive coding kind of circuit, and it is a predictive coding circuit, but the problem isn't solved. So the last step is just how do we solve this problem? And we're going to apply our favorite trick again, but this time inspired by the anatomy of the bulb. So we're actually not doing too bad in terms of anatomy, but we're going to kind of take it a step further. And what we're going to notice, we're going to use the fact that in real life, I've drawn the situation as one glomerulus, one mitral cell. But this isn't actually what it looks like in real life. In real life, you have one glomerulus, so it says Y1, one. But they have dozens of sister cells, called sister mitral cells. So I'll call this Y11, Y12, so on. Y1, N. So it seems like we should be able to kind of fix this connectivity problem if we use these sister cells somehow. Okay, so how are we going to do this? And notice that the inputs are essentially they're electrically coupled and chemically coupled up here. So their inputs are fused, but their interaction with the granule cells are different. That's kind of what in biology gives their different responses. So just the main trick, I'm going to write down my Lagrangian again. So let's just do that. Okay. So recall that we had this Lagrangian that is equal to phi of x minus sigma squared y squared over 2 plus y transpose y minus ax. Okay, so now we're just going to use a very simple property of a phi of x, and phi of x, as I wrote down before, phi of x is beta x1 plus gamma over 2 x squared, etc. Now the cool thing about phi of x is that it is separable. So if I take x and I write it out as x1, x2, x3, xn, and I then just divide this into blocks. Okay, so let's just divide it the way I've shown into one block, so x superscript 1. Maybe the next one's called x superscript 2 all the way to x superscript little n. Phi of x is equal to sigma phi xi, where I equals 1 to n. No problem there. If I similarly split up A, the columns of A, I can write A of x is going to equal to sigma ai xi. Okay, so this is, I've taken the same x's and I've just split up. I've taken the A matrix that I had, and if I I'm going to write it really small up here. So if I had my A matrix, I just lined it up, I lined up my columns, I'm just going to split it along there. The exact same spot. So I'm going to get A1 to AN. Okay? Very good. So now we can just plug in these decompositions into L. And let's see what that does. So I'm going to move all the terms that don't matter for now outside. So lambda. And then, so now we're going to use our decomposition, xi, minus lambda transpose ai xi. Okay, and notice that I'm still using the same lambda. So I haven't done anything yet. You know, this is, the computer science guys like this because, you know, if minimizing this over x is hard to do, you can just pass it out to a bunch of computers, have them minimize in parallel, send back the x's, and then you can do this computation. What we're going to say is we're going to apply our one weird trick, and we're going to introduce sister microcells. So what I want to do is I want to actually give each one of these guys its own lambda. So I'm going to say this is equal to, so this is equal to x, and then now I'm going to be very explicit. And I'm going to some other arguments that I'll introduce in a second. And now the sum is going to go on the outside. Lambda I squared over 2n plus lambda I transpose y over n plus phi of xi minus lambda I transpose ai. So, yes, 2 minutes. All right, so I think this is basically the trick, and you guys can then do the gradients yourselves. So I think this is what I wanted to show you. So the idea here is that, okay, so this will equal to this, such that y equals lambda I for all I. So this is equal to this Lagrangian if this condition holds. So what this will involve is, you end up you end up adding to this term a set of Lagrange multipliers enforcing the constraint. And to get rid of lambda in these equations, you actually add an augmentation term. Should be negative, actually. So this is just going to enforce the constraint. At the solution, this is going to be 0. So all this is doing is allowing you to take the gradient with respect to lambda and eliminate it from the equations. And when you do all of that, you'll end up with a set of equations that just tell you what the sister cells are doing. And it will just involve the sister cells, their inputs, their interactions within their blocks, and some averaging input that they can get from the glomeruli. So you just need to assume that this average up here, the average of these activities is available to all of the neurons, which I think is a reasonable assumption. And so the main point that, the last point that I want to end with, how the whole sparse connectivity thing came about, is now these lambdas, they don't interact with all of the x's. They only interact, if you had that original x vector, the x vector stays the same, but now that you've split it up, these glomeruli are only going to interact with this subset. And these microcells are going to interact with that subset. That's all it is. Okay, so the total number of synapses hasn't changed. You still have to have these guys communicating with these glomeruli, but each one of these cells now is communicating with, n over n granule cells. And you can, it's very easy to show, and you should I hope you're convinced, that this is all solving that original Lagrangian, which is solving the map inference problem. So this whole thing is solving the same problem, but now your connectivity has been reduced by a factor of n at the cost of introducing n times as many cells. So that's basically it. If you want to look at how this actually works in real life, you can come and look at my computer, but I think that was the basic idea. So thanks for your attention.
One very short question.
You still need all the glomeruli to go to all the piriform cells, right?
Yes. So I will need all these microcell to be connecting to all of the cells in piriform. Now, one funny thing in this situation is that at convergence, because we have this constraint, all these systems will have the same values. So you can kind of distribute that load, n times. But yes, you still have to have the full. Yeah.
they're right now, so you can ask